All right, so today's Tuesday, April 21st. This is a regular Zoom meeting, and we're going to be going inferences for means. We will not, this will be only a 1 hour Zoom meeting because I have a meeting afterwards. Plan to try to get through two questions. One of them is very, very long. It was a question 6, an investigative task back in 1999. And will take a while. So with that said, I'm going to go ahead and put that problem up, and immediately you see a long list of data, and I'm going to go ahead and pause this. Well, I'll pause this in just a second. But if you would put the training before into L1, after in L2, L1, L2. So this group goes into L1, this group continues in L1, this goes in L2, and this continues through L2. And I'm going to give you a moment to do that because that does take some time. I'm going to talk about this problem. So the problem is 1999, question 6, and quite frankly, this is early on in AP statistics. And when I say that, it means early on in the creation of AP statistics exams. So there's some things that they didn't require or they didn't do as well, and we'll talk about them because when you go to check the scoring rubric, you'll go, well, that wasn't there. And I'm like, yes, it wasn't there then, but it would be there now. So I'm going to talk about those things as well. But this is actually a pretty good problem, except for the fact that they really kind of mess up conditions based on what they require now. So researchers want to see whether training increases the capability of people to correctly predict outcomes of coin tosses. And each of 20 people, and I guess that's what I should have said, is you should have 20 before trainings, then you should have 20 after trainings. All right, so they have 20 people to predict the outcome of heads or tails of 100 independent tosses of a fair coin. So basically, we have 20 people, each one's going to flip the coin 100 times, and we're going to write down how many times they predicted. Okay, so that's kind of where we're going with this. And so they do it before training, and then after training, they are retested with a new set of 100 tosses. All right, so they have all sets of 40, 100 tosses are independently generated. Now, this is really important to talk about. They say 40 sets. They mean they have 20 sets of before and 20 sets of after. So that's where they're getting the 40 sets. Since the coin is fair, the probability of a correct guess by chance is 0.5. So the numbers for correct for each are 20 people as follows, and the number. So these are the number of correct. So this is a number correct before. This is a number correct after. All right. To answer the following questions, you may want to enter the data into your calculator, and I'll leave this here a little longer. As it checked that you've entered the data correctly, the sum of the scores before training is 1,120. The sum of the scores after training is 1,126. All right, so do the data suggest that after training, people can correctly predict coin toss outcomes better than a 50% expected by chance alone? Give an appropriate statistical evidence to support your conclusion. I'll be honest with you, this could be a little bit confusing for you. Because first off, I look and go, oh, before or after, I immediately think matched pairs. That's the very, very first thing I think of. Then they say, oh, they want to know if it's 50%. So then I think proportions. So I'm like, gosh, what do they want? A proportion, a matched pair? Am I reading this wrong? What do I need to do? So I reread the thing, and I go, you know what? They say, do the data suggest that training can correctly predict a coin toss outcome better than 50% expected? Oh, that means each individual, we would expect each individual to guess 50. All right, that's what we would expect him to guess. Now, could we expect him to guess 50%? Yes, we could have done mu equals 50, or we could have done P for proportion equals 50. We actually have the choice to do either one of those, and either one is going to be correct. I'm going to approach this from the standpoint of a means. If we have time at the end of the lesson today, and I don't think we will, I'll address it from the standpoint of proportion. But from the standpoint of a means, it's like each person, if they, we would expect them to guess 50. All right. So I mean, it's like 50% of the time. If I flip it 100 times, I should guess 50, because the expected value real quickly, not that this is necessary, but I'll show it anyway, is 0.5 times the 100 flips for each person. So I'd expect there to be 50 flips. All right. Okay, so I'm going to hope that you have that answered, and then I'm going to start breaking down this question. So the very first thing is, if I'm doing a hypothesis test and I'm doing it for means, I'm going to write my null, and my null is mu equals 50, and I want to know whether or not can predict outcomes better than the 50%. This is after training. So mu equals the true population mean number of correct points after training. Always must define it. Okay? The next thing, conditions. Random sample. This is where they weren't doing a very good job back then. And this is a random sample, even though they didn't tell us. You can expect on our exam, they're going to tell you that it's a random sample or that it was an experiment and they randomly assigned. So you can expect today on to be random, I mean, for this year, we'll say random sample or randomly assigned, but here it wasn't. So I'm going to say not given, must assume that the sample of 20 people is representative of the population of those predicting coin flips. And I don't know if they are or not, but I'm going to have to assume that, because randomness is extremely important. Should always be there. Make sure you include it, even though they didn't. All right. Then I need to check for the population size. N is less than 20%. So 20 divided by 0.1 is 200. Reasonable to assume that there are at least 200 people predicting coin flips. And that's probably a pretty reasonable statement, because back in elementary and middle school, I know that there are more people than that at my school of guys who actually flip coins. Then I get to do a box plot, which really excites me because it takes time to do. And I've entered the data into L2, and I probably should have labeled this correct predictions after training. All right. And Q1, the median, Q3, and Q4. Actually, I don't need Q4, but that's the max, excuse me. All right, so Q1, median, Q3, max, min. The one thing I notice is I don't see any outliers. And they had an interesting statement. The box plot has no outliers and is not excessively skewed. And so if you see something, because sometimes they have some data that looks kind of skewed, the box plot has no outliers, make sure it has no outliers, and then say it's not excessively skewed. So that kind of clears away the skewed problem. And the data appears to be normal enough is my statement. So the data appears to be normal enough. And since we're going to have to use a standard, we don't have the standard deviation of the population, we're going to be using a t-test because we're using S for the sample. All right. And the formula is x bar minus mu, standard deviation, divided by the square root of n. All right, so x bar minus mu, standard deviation divided by square root of n. Well, I don't have an x bar yet, so I need to calculate it. And x bar equals the observations, or the sum of the observations. So when I sum up all the values in L2, and I get 1126, divided by 20 is 56.3. And this should have said not 56.4, that should say 56.3. So we're looking for the probability that t is greater than 56.3 minus 50 divided by the standard deviation. And I got that because I went ahead and ran the test. I went stat test, t-test, and I actually have data. The mean, in this case, is 50 because we're claiming that that's what we claimed above. And my list of data is an L2. My frequency is 1. And once again, the alternative was greater than, so I need greater than checked on the calculator, which is what I have. And I calculate, and there we go. I end up getting a t statistic of 5.963. It gives me my standard deviation, which apparently I did not input the right standard deviation. So I need to make that correction. Let me make that correction real quickly. This should have been 4.725. So this would mean probability that t is greater than 56.3 minus 50 over 4.725 over the square root of 20. And when I do that, I get a super small p-value. Please be careful. Make sure that if you have a number greater than 1, you recognize this in scientific notation. Now, in this particular case, if you'd want to put approximately 0, that would have been perfectly acceptable. Once you get to 4 zeros, you don't need to do this. I went ahead and wrote it out just so we could see it, but we didn't have to. We could just set approximately 0. I went ahead and explained my p-value briefly. So because my p-value is so small, it's going to be less than alpha. We're going to definitely reject the null. So there's a almost 0% chance we'd get a test statistic like this, given that the average number of correct coin predictions after training is 50. That's my definition of p-value. That's actually not my conclusion. My actual conclusion is our p-value is this, or almost 0. We reject the null. There is sufficient evidence at alpha equal 0.05 to suggest the true population mean for the number of correct coin predictions after training is greater than 50. So basically, after training, if I were to write a simplified statement, after training, we'd expect them to get more than 50 right if they flipped it 100 times. All right. So that was part A. And that was a whole lot of work. Do you all have questions in regards to part A? Is there anything in there that didn't make sense? Because I actually had a couple of errors in there myself. Okay, so moving on. Back to part B. Part B, does the statistical test that you completed in part A provide evidence that this training is effective in improving a person's ability to predict coin toss outcomes? If yes, justify your answer. If no, conduct an appropriate analysis that would allow you to determine whether or not the training is effective. Well, for me to determine whether the training is effective, I would have to know what they were doing beforehand. How good were they beforehand? Now with coin tosses, it's a little more confusing, but if I wanted to know if you're better at shooting baskets, I'd have to know how bad or good you were before you started and how bad or good after you started. And so I'd have to compare those. So that means I would have to do a difference of means. All right, so first off, I need to answer their question. Their question was, does it provide evidence that the training is effective? And I need to say if it does or doesn't, and why. So the test in part A does not provide evidence that the training was effective because we did not compare the before training predictions to the after training prediction results. In other words, it's possible that these guys were already good coin toss predictors. I don't know why that's possible, but it could happen. Okay, maybe they're used to gambling. Not that anyone would gamble, because that would be wholly immoral. And as a public school teacher, I would never suggest that we do anything that fun. I mean, that immoral. So if we are doing a test for mean differences, or a paired test, this is going to be 0, except for very, very special cases. And I think they would let us know if that was the case, if it was different. Now, I did less than 0 because I did before minus after. All right, mu d equal the true population mean difference of coin predictions before minus after. Had I done before, after minus before, I would have been looking for greater than 0. So it depends. This is what determined my alternative. So in other words, if I'd swapped the order, it would have been greater than. If I'd done after minus before, that would have been perfectly acceptable. It just would have been greater than. So anyway, conditions, random sample. Once again, not given. Must assume that the sample of 20 is representative of the population of those guessing. 20, once it's reasonable, assume that there are at least 200 people. But here and that's the same as what we had before. We need to add that the differences are independent. This is something we didn't have. And basically what that means when we say the differences are independent, it means you're being able to guess before and after correctly should not impact my being able to guess before and after. So those differences between my guessing and your guessing should be independent. And that's reasonable. All right. So then we have a box plot that looks a bit different. And here's why. So I go to stat edit and I see that I have my data in there. Well, I need the data of the differences, because over in L1 I have the before training, L2 is the after, but I need before minus after. So second 1 minus second 2, and that populates my differences. All right. So then I go to the second stat plot, make sure it's turned on, which arrow to the left, calculate, select the one with the box plot with dots. My X list should be L3. And then I can go ahead and press zoom 9. And there I get that. And somehow or another, mine's off. My drawing is off. That's wrong. 3.5, that's right. My median's in the wrong spot. Okay, so my median's in the wrong spot. Now, this is the one thing that I noticed about this. This should have been my median. When I look at this, I can make an argument for being skewed, because this side is definitely longer than this side. However, this is what they say. The box plot has no outliers and is not excessively skewed. The data appears to be normal enough. So while I like that, I don't. I don't like that at all. Okay. I don't need that. So here we go. Stat, test, t-test. Once again, I have data, but now my mean is based on my null hypothesis, which is 0. My data list is no longer an L2, it's an L3. And here we have a less than, so I need a less than symbol calculate there as well. So I'm then going to press calculate. And when there, I can start plugging into my formula. X bar of the differences minus the mean difference, standard deviation of the differences divided by the square root of n. So X bar of my differences is 0.3, standard deviation 6.837, sample size 20, And we already said that our mean was 0. So there's that information. And when I did that, I ended up getting a p-value, a t statistic of negative 0.1962. And I should have done this before, but I didn't. 0. We have negative 0.196. So I'm looking for this area. Well, it turns out this area is actually pretty big. It's 0.4233. That's much greater than 0.05. So consequently, we failed to reject the null. There's a 0.4233 chance we'd get a test statistic like this, given that the mean difference in coin prediction before minus after training is 0. This is my definition of p-value. And our p-value is 0.4233. We failed to reject a null. There's not sufficient evidence at alpha equal 0.05 to suggest that the true population mean difference in coin predictions is less than 0. There is not sufficient evidence to say that there was an improvement in coin predictions after the training. So in other words, after training, there wasn't significant evidence to say that there was a difference between before and after, but part A was significant. And the reason must have been is these guys must have already been good guessers to begin with, and this training didn't help them. So the first time they took it is like, hey, you're already doing better than 50%. But after we took the training, it really didn't change things that much. So these guys obviously were good coin guessers to begin with. All right. Part C. Would knowing a person's score before training being helpful in predicting his or her score after training? Justify your response. Well, here's the deal. They want me to predict the score after training. So that means there has to be some sort of relationship between before minus after. That makes me think for this class, that makes me think about regression. Because regression, we'd have something like y hat equals a minus or a plus bx. That's what, and so in this case, I would go, you know what, what's the probability of after training equals a plus b times before training. Now, they didn't tell me whether it was a linear equation or not. So they didn't say whether I needed to do regression or not. Matter of fact, I didn't have to. I just need to find out whether or not I can look at the befores. So can I look at these before scores and make a prediction about each individual's after? Based on this 46, could I get close to 61? Based on this 48, can I get close to 62? And really, that's kind of a tough question to do without knowing where you're headed. So once again, we're looking to see whether a relationship exists between the scores. And what I would do, and what the easiest thing to have done, would have been going to second stat plot and go ahead and select the scatter plot and see if there's a pattern. So my X list is an L1 and my Y list is L2. And the reason it's L1, L2 is I want to see if the before predicts the after. And then I just do a zoom 9. And I don't know about you, but that looks like a complete random set of dots. I don't see a pattern there. All right. And so the scatter plot does not show any obvious relationship, does not show any pattern between the two variables. All right. Therefore, knowing a person's score before score does not help this person's after score. Because the scatter plot is random, and you can say the scatter plot is random and does not show a pattern, I could not make any prediction. I'm going to pause the recording for just a moment. And we're going to move on to our next problem. This will be the last problem for today because of the meeting that I have after this. We will finish we will do the next 3 problems on Thursday. There will be a Stat Saturday this Saturday, and its primary focus, well, almost all, I guess all of it, is on some sort of probability. So it'll all be on probability this Saturday. So you probably want to attend for that. So this one is much more straightforward, much more typical problem. I would definitely expect problems of this level of difficulty. So patients with heart attack symptoms arrive at the emergency room either by ambulance or self-transportation provided by themselves, family, or friends. When a patient arrives at the emergency room, the time of arrival is recorded. The time when the patient's diagnostic treatment begins is also recorded. Administrator of a large hospital wanted to determine whether the mean wait time between arrival and diagnostic treatment for patients with heart attack symptoms differs according to the mode of transportation. So in other words, if I ride by ambulance, is my treatment time, my time from I arrive to the time I get treated longer or shorter than or no different than if I drive myself or my family or friends take me? A random sample of 150 patients with heart attack symptoms who had reported to the emergency room was selected. For each patient, the mode of transportation and the wait time were recorded. Summary statistics for each mode of transportation are shown in the table below. So we see 77 people rode by ambulance, 73 arrived, they either drove themselves or had their friends, and we have their wait time. So when I just look at this right away, I sit there and go, there is some evidence that there's a difference. It appears that if you take yourself to the emergency room, you're going to have to wait a little bit longer on average than those who arrive by ambulance. This is what it appears, but that's not statistical evidence. We're going to need to run some sort of test. So in this particular case, they said using a 99% confidence interval to estimate the differences between the mean wait times for ambulance transported patients and self-transported patients to this emergency room. So they're specifically saying run a confidence interval. They say run a confidence interval, you don't have the option of running a hypothesis test. Could you run a hypothesis test? Yes, but in this case they said run a confidence interval, you got it, so you have to do it. Okay, once again, we have a sample. And so since we have a sample, these are sample standard deviations. This means I'm running a two-sample T because I'm using the standard deviation from the sample. All right, so first off, start off by writing my null alternative hypothesis. Mean time arriving by ambulance is mean time arriving by self. And then I want to know, is there a difference? Because they said estimate the difference. All right. So I need to define mu A, mu S. Mu A is the true population mean times for arriving by ambulance. Mu S is true population mean waiting for arriving by self. Conditions, independent random samples. Please note that if you're working with a 2-sample test, make sure you include the word independent. So if there's 2 samples involved, I don't care if it's proportions or means, make sure it's independent. Make sure the samples are independent. Independent sample for both means of transportations were taken. This is given. They said it above. N is less than 10% of the population. Reasonable to assume that there are more than 770 heart attack victims taken to the hospital by ambulance. And we also do the same thing that are taken by self. And so we go, hey, you know what? That's reasonable. And the reason we do that is because we're doing this without replacement. And because we're doing without replacement, we're making sure that the individuals are not impacting it. And so while it changes the percentages slightly, it doesn't have a great impact. I know I always go back to the same scenario, the giant pile of M&Ms. I take away a red one, and technically the percentage changed, but it changed so slightly we don't care about it. So as long as it's less than 10%, it doesn't impact it that much. In both cases, we have sample size greater than 30, so the distribution of means is normal by central limit theorem. Please use the word approximately. So the distribution of means is approximately normal because n is greater than 30. My formula. All right, and by the way, you'll have access to my notes, so the formula chart's in the back of my notes. Whenever they have me run a confidence interval or do any of these, I actually run the test right off at the get-go. So here we go. Second quit, stat test, 2 sample t interval, and I know I have to scroll a ways. I don't remember where it is. Oops, I went too far. 2 sample t interval. And this time we're using statistics. And I'm going to go back to my table because that's where it initially was. So my mean for was 6.04. My standard deviation is 4.3. My sample size is 77. 8.3. Standard deviation for self is 5.16. Sample size is 73. And they want a confidence level of 0.99. So I'll put in 0.99. And make sure you note the degrees of freedom, because what you're really going to write, so here's my degrees of freedom. You're actually going to write and leave a space for that. You're going to have to come back and fill that in. All right, but the degrees of freedom that we calculated from the calculator did it, was 140.37. All right, so I can go ahead and write my interval. I can go ahead and fill in everything but this value right here. So now I need to go, because this value is not given to me, my t star. I need to go back and calculate t star. So here's how you do t star. Second vars, inverse t, parenthesis 1 minus 0.99, close parenthesis, divided by 2. Degrees of freedom, 140.37. And I get 2.61. All right. So we got to interpret our interval. We are 99% confident the true population difference in mean wait times for the difference in ambulance minus self lies within the interval of this. So basically, if you ask me to predict, hey, where does the difference lie, or what's the difference? I'd say, oh, somewhere between here and here. I'm 99% sure it's between 4.3 minutes and 0.2 minutes. All right, with ambulances having a shorter wait time. Part B, based on this confidence interval, do you think the difference in mean times is statistically significant? Okay, so if I were to write a whole the hypothesis test for this, this is what I'd write. And 0 is not contained within the interval, which indicates the difference in wait times based on the mode of transportation to the hospital is significant at alpha equal 0.01. Why did I choose alpha equals 0.01? Because 1 minus 0.99 equals 0.01. We can conclude that the wait times for those who were taken by friends or family was greater than those that were taken by ambulance, because the interval is negative, indicating that those taken by ambulance had less wait time than those taken by family and friends or transported by self. All right, I'm going to